Good afternoon. Welcome to the HiPEAC virtual conference. I am Diana Marculescu. I'm a professor at the University of Texas at Austin, and I'm the general chair of this conference. Next. We're really pleased to have a lot of our sponsors listed here. We're very thankful for their support. And just a reminder, all these sessions of this conference will be virtual, as I mentioned, and today is our first day. Next. In addition to me, there are many people who have dedicated their time, effort, and knowledge to put together the program for this conference. I'm pleased to introduce the program chair, Cristina Silvano, with the Politecnico di Milano in Italy, and also the workshops and tutorials chair, Sasha Urig, with Airbus CRT in Germany. Next. We also are very thankful to the many people who have put together the program and organized the conference. The industrial session chair, Daniel Garcia Perez, poster chair, Con de Busser, sponsors chair, Vicky Wendels, web and registration chair, and also the person who is behind putting together this virtual session and all the other virtual sessions, Eneko Ilaramendi, local arrangements chair, Peter Santo, publicity chairs, Diego Lanos, De Zundong, the Gaspar Moraporta, recruitment chair, Xavier Salazar, finance chair, again, Vicky Wandels, and communications chair, Kath Roderick. And with this, I would like to give it to Con de Busser. Con, you're muted.
Yes, I'm muted, sorry. So my name is Koen de Busser. I'm poster chair of this discussion, but I'm also the coordinator of the HiPEAC network. And I would like to start with some sad news. When we started the program, we had two general chairs. The other one was Bela Feher, who is from the Budapest University of Technology of Economics. But unfortunately, in September, he got COVID, and on October, the 2nd of October, he passed away. Bela was a very active HiPEAC member. He also founded the FPGA Research Lab in Budapest. He was an esteemed engineer. He was he was an optimist and also a very kind person. And we all miss him. And I propose that we observe a little bit of science to remember Bela. Thank you. This conference has been organized for almost 20 years now. This year is a virtual conference. We have keynotes and a paper tag, but also a very important industrial session, also an industrial exhibition, and we have a whole lot of workshops and tutorials. Here you have an overview of the workshop. There are 29 workshops. I'm not going to read them. There are many. If you are registered for the conference, you can attend any workshop or tutorial that you want. You just have to register for it, and you get the Zoom link and you can enter the session. There are no limitations of size of rooms and things like that in the virtual conference. These are the 6 tutorials that we have. If you are interested in one of these topics, feel free to register and to attend them, to participate in them. Tomorrow we have an industry day, only on Tuesday. We have more than 100 industry participants in this event. There will be an industry session in the afternoon with 12 industry talks, starting after the keynote at 3 o'clock. Here you see the logos of the companies that will talk there. There will also be a virtual exhibition. We have 16 virtual booths from industry and also from a number of European projects. And then we also have finally a virtual recruitment booth. If you are looking for a new job, if you would get in touch with some of the companies, feel free to visit the virtual recruitment booth and to talk to our recruiters. How can you visit the virtual exhibition? Well, you go to the program and then you have here the tab exhibition. Within the exhibition, you can join the virtual exhibition. We are using a different platform for the exhibition. For the booth, it's called Brazen, and you have to register. Registering is very simple. It's just entering your name, your email address, and that's about the password, and that's about it. And then you can freely roam from one booth to another and to chat with the people in the booth. We also traditionally have a poster session. This year it's a virtual poster session. We called it the poster gallery, and there's only one project who makes use of it. They present 50 posters of so-called technology transfer experiments that they carried out over the last 3 years. So if you're interested, you can definitely attend them. Some of them are also presented in the teaser workshop this afternoon. These are, again, the list of the sponsors. I would like to thank all the sponsors to make this virtual event possible. And this allows me to give the floor to the program chair, Christina.
Thank you very much, Koen, for introducing me. Here, there are the record number of participants we had this year to this virtual event. We hope to reach more than 800 participants by the end of the event. The next.
Sorry.
How to attend events. So each one of you can update the registration at any time, and this enables you to access the Zoom session you would like to attend. So please update if needed your registration. Next. Next. Okay, so the program today includes 3 keynotes and 35 technical papers. Today we'll have our first speaker, Evangelos Eleftheriou from IBM Research Zurich. Then tomorrow, Brad McCready from AMD in Austin. And Wednesday, we will get Tulika Mitra from the National University of Singapore. There are, as I say, 35 paper presentations organized in 6 tracks. And each day we have 2 tracks. The first track is starting at 3 p.m. in the early afternoon, and the second track will start at 5:30 p.m. each day. As you know, HiPEAC is a journal-first conference based on ACM TACO, Transactional Architecture and Code Optimization. So let me remind, first of all, that ACM TACO is using an open access policy, so you can freely access any paper in the program from the web. Next. In this slide, you can see the number of submissions we have received. Practically, submissions were accepted from June 2019 up to June 2020 with a 2-round revision process. This year, we have received 121 submissions. And finally, after the decisions of the editorial board chaired by David Caeli, we got 44 papers accepted. And then we have invited 35 original paper work, that means papers not yet presented at any conference, to be presented here at this event. As you can see from this slide, this is a regional breakout of the technical papers, and you can see how HiPEAC is a truly international conference, and this year we got practically 1/3 of the papers accepted from Asia, 1/3 from America, and 1/3 from Europe. So this is our general introduction, but now I'm very glad and honored to introduce Evangelos Eleftheriou. He had his PhD in electrical engineering from Carleton University in Ottawa. Then he joined the IBM Research Lab in Zurich, and now he became a department head at IBM Research in Zurich. His research interests include signal processing, coding, non-volatile memory technologies, and emerging technologies and computing paradigms such as neuromorphic computing and in-memory computing. In 2002, Evangelos was appointed a fellow of IEEE and IBM fellow. At the same year, he was also admitted to the IBM Academy of Technology. Over the years, he was a recipient of several international awards. And among them, in 2016, he received an honorary professorship from his alma mater, University of Patras in Greece, and was admitted to a US National Academy of Engineering as a foreign member. So, welcome, Evangelos, again, and the floor is yours. I'm switching off my video.
You're muted, Evangelos.
Evangelos, you are muted.
Okay.
Okay, now it's fine. Thank you.
Okay, very good. I'm really sorry. So thank you very much, Christina, for your kind introduction. Good morning, good evening, good afternoon to everybody, wherever you are. So it's really a great pleasure to be with you here today. My talk will focus on the emerging field of in-memory computing and how these recent developments drive innovation in computing systems. Technology is progressing at an incredible pace, and no technology is moving faster than artificial intelligence. The mouse. Clearly, AI is reshaping our lives. One can use AI technologies either to automate or to augment humans. In the last 5+ years, AI has become synonymous with deep learning. And the progress in this area is fast and dramatic. We are at a point where, for example, image and speech recognition can produce accuracies close to or better than the human brain. Most of the fundamental algorithmic developments around deep learning goes back decades. However, the key reasons of the recent success are the availability of large amounts of data for training the neural networks and the immense compute power. The graph on the right-hand side shows the amount of compute used in the largest AI training runs in petaflops per second day. A petaflops per second day consists of performing 10 to the 15 neural net operations per second for 1 day, or a total of about 10 to the 20 operations. We can see that the amount of compute has been increasing exponentially. From AlexNet, that was introduced back in 2012, until AlphaGo Zero from Google, which was introduced around 2018, there has been a 300,000 increase in compute. Alternatively, the compute requirements for really large AI training jobs are doubling every 3.5 months. Clearly, this is unsustainable without fundamental hardware and software innovations. It's interesting to look a little bit more carefully into the breakdown of the operation types within deep learning. As you can see on this graph, for the 3 most common AI applications, such as speech recognition, natural language processing, and computer vision, which involve RNNs, LSTMs, and CNNs, the matrix vector multiplications constitute 70 to 90% of the total deep learning operations. The rest of the operations are simple element-wise operations with single or multiple word operands. A consequence of the continued increase of the compute requirements of AI applications is that the power consumption and the time to insight are increasing as well. For example, here is training an image recognition model. It is a ResNet 101. This means 1001 layers. And we use the ImageNet 22K dataset, which includes 22,000 of classes. If we use 4 GPUs, it takes 16 days and approximately 385 kilowatt hours. We can speed up training by using 256 GPUs, albeit the power now also increases to 450 kilowatt hours. One model training run is approximately 2 weeks of home energy consumption. The core issue is moving data. Moving data or shuttling data between the processor and the memory in the conventional von Neumann compute architecture. Now, when you move data, then there is a cost for every data transfer. And you see on the right-hand side that if I want to transfer data from a DRAM, then the energy consumption is 640 picojoules per word. Then if I go down to the SRAM, then it is 50 picojoules. And then when I have a small local SRAM, then it is about 5 picojoules. So compare this energy consumption for data transfer to the cost of an 8-bit multiplication. So it is only 0.2 picojoules, which is a factor of about 3,000 less than transferring data from DRAM. Although this study was back in 2014 for the 45 nanometer CMOS technology node, there are even recent studies that show that the problem gets exacerbated as we move down the lithography node. However, it's not only AI in the cloud, but also AI at the edge, which is becoming the next revolution. And there is a wealth of applications at the edge. For example, AI for mobile devices. There is embedded processing for the Internet of Everything, or the Internet of Things. Embedded processing for prosthetics, wearables, personalized healthcare, not to mention the real-time video analytics for autonomous driving. However, all these embedded applications are energy and memory constrained. Thus, efficiency matters even more so at the edge. Summarizing, we observe 3 main trends of computer systems for AI applications. First, data access is a major bottleneck. Second, energy consumption is a key limiter. Third, energy to move data dominates compute energy. These trends open up new opportunities towards designing future systems, minimize data movement for performing computation directly or near where the data resides, and second, introduce novel computational primitives like matrix vector multiplication that facilitate the deep learning workloads. There are many new technologies that drive innovation in computing systems. For example, the adoption of storage class memory in the memory hierarchy, the advent of 3D XP from Intel, a typical storage class memory technology, developing new horizons for running faster and with lower power requirements, many applications. Moreover, the latest generations of accelerators like GPUs or ASICs employing mixed precision arithmetic and operating in conjunction with 3D stacked DRAM have resulted in highly efficient systems. In-memory computing is a novel non-von Neumann computing paradigm aiming at collocating the memory with the compute operation. This will also drive innovation in computing systems. So let's have a look at this very simplified schematics. On the left-hand side, we have the traditional non-von Neumann computing architecture. It comprises a processing unit and a memory subsystem. Data A is stored in one of the banks of the memory, and we want to operate or execute the function f on this data. Then we have to fetch the data to the local cache. We have to apply the function f with our ALU and then store the data back into the memory. That's exactly where we have the problem. It's the well-known von Neumann bottleneck. On the right-hand side, we have the new computing paradigm of in-memory computing. We have, again, a processing unit. We also have a memory, but now the memory comprises the conventional memory, but also a new, in quotes, memory, a computational memory. Now, when I want to execute an operation, the data which now reside in the computational memory stay there, and under the control of the control unit, the function f is executed in place using the physical attributes of the memory technology. Several computational tasks, such as logical operations, arithmetic operations, and even certain machine learning tasks can be implemented in such a computational memory unit. The memory is not just a place where you park your data, but an active participant in computing. Now we're talking about memory, computational memory. And here we see the various incarnations of memory. On the left-hand side, we have the classical, DRAM, SRAM, flash, where information is stored as charge. In DRAM, we have an explicit capacitor. In flash, we have the floating gate. If I want to do computation, we use the Coulomb's law. Now, on the right-hand side, we have these emerging memory technologies under the name memristors, where information is stored as resistance. Typical examples are the metal oxide memories or the phase change memory, like the one that is being used in 3D XP by Intel. In this case, if I want to do computations, I rely on Ohm's law and Kirchhoff's law. Clearly, these memory technologies, and in particular, the new ones, the emerging ones, are significant for the memory and storage hierarchy. However, they also possess sufficient richness of dynamics for non-von Neumann computing. There is a range of in-memory logic and arithmetic operations that can be performed using both charge-based and resistance-based memory devices. This slide shows examples of logical operations. On the left-hand side, we can see schematics of a bitwise AND and OR operations using two memory devices. Data are stored as resistance logic state variables. Then, with the appropriate choice of the current thresholds in the sense amplifier, it's possible to implement AND and OR logical operations. On the right-hand side, we can see schematics of, again, bitwise AND and OR operations using DRAM and SRAM cells. In the case of DRAM, the operands are stored in the cells A and B, and then there is a third DRAM cell that plays the role of a selector, which uses to decide whether AND or OR is realized. And below you have, again, AND and NOR operations, which are performed by using SRAM, by sensing the bit line or the complement bit line with appropriate voltage references at the sense amplifier. Another very important arithmetic operation in machine learning and deep learning is matrix vector multiplication. Here, the memory is arranged as a crossbar array, and at the cross points, there are resistive memory elements. It could be phase change memory or resistive RAM. Let's assume now that I want to perform a matrix vector multiplication. On the left-hand side, you see a matrix, 3 rows, 2 columns, multiplied by a 2-dimensional vector. The result is a 3-dimensional vector. So what we do is we map the values, the elements of the matrix into conductance values on the crossbar array. We exploit, in other words, the analog storage capability of the resistive memory. Then we map the read voltage, we map the 2-dimensional vector into the read voltage at the input of the crossbar array, and the result automatically appears as current at the columns of this crossbar array. Therefore, I can have in-place matrix vector multiply with time complexity of 0.1 time complexity. And you can do the same thing for the transposed matrix and vector multiplication. In this case, you just apply the voltages, you apply the voltages at the columns, and you get the currents at the rows. Now, what is the precision we can get out of this analog matrix vector multiplication? This is an example of multiplying a 256 by 256 matrix, which has elements drawn out of a Gaussian distribution. Those values are coded into a phase change memory chip that you see on the left-hand side. This is the IBM's first generation analog AI chip. It has 1 million PCM devices, and it is a 90 nanometer CMOS technology. Then we have also a vector X, which is a 256 long Gaussian vector, which is applied as voltage on this PCM chip. Then we have this plot. On the x-axis, we have the exact value of the BIs, the result of this matrix vector multiplication. And on the y-axis, we have the estimated BI values. Now, ideally, if we had a floating point full precision arithmetic, it would have been a straight line, the black line. But instead, you see those blue circles around the straight diagonal line. Now, we did the same experiment by implementing a 4-bit fixed point multiplication on FPGA. And lo and behold, the precision of the PCM devices, these first generation PCM devices, is equivalent to a 4-bit fixed point arithmetic. Of course, you can do similar things by using the standard SRAM. This is another example of multiplying a matrix by a vector. In this case, just for explanation, we have used a binary matrix. So we store the elements of this binary matrix into the SRAM cells. Then the elements of the 2-dimensional vector are mapped into the capacitor voltage, and the result of the matrix vector multiplication appears as a voltage on the bit lines. So the switches and the way the sequence of the switching events is described below. So the step 1, you charge the capacitors with the input value. In a step 2, the values associated with 0, the capacitors associated with 0 value are discharged. And in the third step, using charge sharing, the capacitors are shorted along the columns, and you get the result. So again, 0.1 time complexity, you can have matrix vector multiplication. Of course, you can have more complex designs than binary arithmetic. So here is a very recent result of a int8 analog Mac engine, 512 by 512, implemented in 14 nanometer technology. So this architecture is scalable in the sense that the precision scales linearly in area, time, and power. On the graph, we've plotted the normalized fixed point Mac output and the normalized analog Mac output. As you can see, since the arithmetic now is 8-bit, 8-bit weights, 8-bit activations, then it's almost impossible to discriminate the difference between the fixed point arithmetic and the analog arithmetic. If you zoom in at the center, you see the ideal fixed point as a almost straight line, and then around it, some noisy outputs. The bottom line is that by digitizing the output of the analog matrix vector multiply Mac with an 8-bit ADC is almost as good as truncating the output of a full precision fixed point Mac to 8-bit. So what can we achieve with all these in-memory logical arithmetic operations? Well, there are many applications that can benefit from in-memory computing. This slide shows a high-level overview of the main applications that are being researched for in-memory computing. On the y-axis, we have computational complexity. And on the x-axis is computational precision. The size of the bubble indicates data motion applications which are heavy in moving data between memory and compute subsystem. Now, on the left-hand side, you see applications like stochastic computing and security, random generators, which require low degree of precision. Also, there isn't high transfer of data. And as you go towards the right-hand side, scientific computing, then we have deep learning training, as well as solving linear and partial differential equations. The problems that could benefit the most from the complexity reduction are the NP-hard problems that involve combinatorial optimization. Data-centric applications in machine learning and scientific computing benefit the most from reduced memory access. Now, going forward, I will only detail a little bit the application of deep learning, specifically inferencing and training. In-memory computing for deep learning has been realized by using various memory technologies. There are many experimental chips based on either memristive technologies or charge-based memories. On the left-hand side, we have the work of Biswas, Valavi, using SRAM, recent work. Then below, we have, again, in-memory computing for deep learning using Flash. There is a well-known famous startup in the US, Mythic, that uses NOR Flash for in-memory computing. On the right-hand side, we have memristive technology. On top, resistor-RAM, and below, PCM, the works of Ambrosio, Sebastian here in Zurich, which is IBM work focusing primarily on phase change memory. I will start with deep learning for inference. This is a high-level block diagram that shows the basic architecture of a deep learning inference engine, which comprises a network of crossbar arrays or computational memory cores that can efficiently implement scale-out neural networks. In this case, the trained synaptic weights are mapped to this array of computational memory cores to perform matrix vector multiplication operations corresponding to each layer. Now, three important remarks. There is no transfer of synaptic weights from memory. all the weights are stored in the crossbar arrays of this kind of data flow reminding engine. Second, all the matrix vector multiplications are performed with type complexity of 01. And since this is similar to a data flow engine, we can exploit this for optimal pipelining. This, in fact, is a pure non-von Neumann machine. Now, a couple of examples. How does it perform? Now, here is an example of a ResNet convolutional neural network with 32 layers, which is trained on the Cypher-10 image classification. Due to the device variability and noise, the network needs to be trained in a specific way so that transferring the digitally trained weights to the analog resistive memory devices will not result in significant loss in accuracy. A custom training approach was developed based on injecting noise to account for the conductance distributions. Injecting noise when you do training is not only unique to in-memory computing, it's a technique that also has been used in mixed precision standard von Neumann accelerators. So this methodology was basically introduced to train this specific ResNet 32 CNN and resulted in an accuracy of 93.71, which is only 0.14% lower than the floating point 32 baseline. Therefore, it is possible to achieve software equivalent classification accuracies using a PCM-based inference engine. Now, since PCM is well known to suffer from drift effects, there has been another experiment to show how the trained network behaves with time. Now, in this case, you have to apply also drift compensation techniques. And as you can see from the dark blue triangles, you can have an accuracy that stays almost flat across, the time axis. So we have in the lab, and you will see later on, a prototype which was programmed 2 years ago, and we still have faithful classification. Of course, one can use also SRAM as an inference engine. This is another example based on an int8 arithmetic, 8-bit for activation, 8-bit for the weight, and analog MAC. So in this particular simulation result, we use PyTorch, and we changed in the library the convolutional kernel with the noisy convolution. So this int8 model with the noisy convolution achieves only 0.26% lower accuracy compared to ideal noiseless model. In this particular case, there is no retraining or recalibration of the model. So the 8-bit weight, 8-bit activation precision is adequate to get as good performance as almost as good performance as the floating point 32 without any training or retraining or recalibration. Just it's a drop-in model. I try now to show you some of the power efficiency results of the various experimental platforms that have appeared in the literature over the last 1 to 2 years. So you hear the metric is teraops per watt. So the most efficient design is this SRAM 1-bit input, 1-bit activation, like a binary correct network with 658 teraops per watt. And in terms of precision, the SRAM system that I described before with 8-bit activation, 8-bit weights gives you a 12 teraops per watt. There are also other designs with NOR flash in the ballpark of 10 teraops per watt, the resistive RAM with analog input, 8-bit activation, and so on and so forth. Now, training. You can also use in-memory for training. Now, in this case, the synaptic weights reside in the computational memory as before, because no high precision is required. And therefore, we perform the forward and backward propagation using the computational memory. However, the weight updates require high precision. These are accumulated in a high precision subunit. The programming pulses are issued to the memory devices and alter the synaptic weights in place. This is an experimental result. You can see on the right-hand side, accuracy, almost as good as training with a 64-bit floating point precision. And below, you see the accuracy over time. This is the prototype that I mentioned before, which is in the lab now for 2 years. For this experiment, it's a very simple network. We've used the previous first-generation PCM chip that we discussed, and 2 PCM devices in a differential configuration. You can go online, you can access this demo environment in our lab through the cloud, the IBM cloud, and you can play with character recognition yourself. Just write down this URL. There is also a photonic counterpart to electronic in-memory computing. A couple of years ago, a photonic memory device was proposed based on phase change materials. Recently, it was shown that by organizing these photonic memory elements in a crossbar configuration, it's possible to perform matrix vector multiply operations. Unlike its electronic counterpart, the wavelength division multiplexing capability can be exploited to perform several matrix vector multiply operations at the same time. Photonic in-memory computing has the potential to achieve petaops per square millimeter compute density and could target applications that have stringent requirements on latency. Is not, though, as power efficient as its electronic counterparts. Closing, we believe that we will see 3 stages of innovations that take us from the near term, where the accelerators are built with conventional CMOS based on the approximate computing paradigm, towards a period of innovation involving in-memory computing using arrays of analog memory elements, and ultimately, who knows, to the era of biologically plausible networks. These latter 2 application areas represent an extremely rich and interesting research space. As a punchline, in-memory computing is poised to have a significant impact on improving the energy and area efficiency, as well as the latency compared to conventional computing systems. Thank you very much for your attention.
Evangelos, thank you so much for being with us today, answering our questions.
Thank you very much.
And let me invite all the people to join the technical sessions. And the first technical session starts in a couple of minutes on compilers. There is the main track starting in a couple of minutes on compilers. So please switch to that room or any other workshops and tutorials in the program for today. Thank you for attending this first session and this first keynote, and see you later on other sessions. Bye-bye. Bye-bye, everybody. And thank you for the questions you posed on the question and answer window. Thank you very much. Bye-bye.